Hey everyone, today we're tackling a LeetCode problem called Count Complete Subarrays in an Array. It sounds a bit technical, but don't worry, we'll break it down together step by step. The goal is to count certain types of subarrays, and we'll figure out exactly what makes a subarray. Ready? Let's dive in. Okay, so here's the official problem statement. Basically, we're given a list of positive numbers. We need to find how many subarrays. That's just a continuous part of the original list are. What does mean here? It means the number of different or distinct numbers inside that subarray must be exactly the same as the number of different numbers in the entire original list. Simple as that. We just need to count how many subarrays satisfy this condition. The constraints tell us the list won't be supermassive, maybe up to 1,000 numbers long. Let's walk through the first example. The list is 1, 3, 1, 2, 2. First, how many different numbers are there in this whole list? We have 1, 3, and 2. So that's 3 distinct numbers. Our target number is 3. Now we look at all possible subarrays. Does 1, 3, 1 have 3 distinct numbers? Nope, just 1 and 3. How about 1, 3, 1, 2? Yes, it has 1, 3, and 2. That's 3 distinct numbers, which matches our target. So that's one complete subarray. We keep checking. 1, 3, 1, 2, 2. Also has 1, 3, and 2. That's another one. 3, 1, 2 also works, and 3, 1, 2, 2 works too. If you check all the others, none of them have exactly 3 distinct numbers. So we found 4 complete subarrays in total. Now for the second example. The list is just 5, 5, 5, 5, 5. How many distinct numbers are in the whole list? Only one. The number 5. So our target is 1. Now let's look at the subarrays. 5 has one distinct number, complete. 5, 5 has one distinct number, complete. 5, 5, 5. Still just the number 5, so one distinct number, complete. In fact, every single subarray you can make from this list will only contain the number 5, meaning they all have exactly one distinct element. How many subarrays are there in a list of length 4? It turns out there are 10, so the answer is 10. Okay, so how could we approach this? The most straightforward way. Well, we first figure out the target number of distinct elements, let's call it by looking at the whole array. Then, we could literally generate every single possible subarray. For each one, we count how many distinct numbers are inside it. If that count equals, we add 1 to our total result. That makes sense, right? But, if the list is long, say 1,000 numbers, generating all subarrays takes quite a bit of time, something like n squared subarrays. And counting distinct elements in each could take up to time too. That sounds like n cubed overall, which is probably too slow for the given constraints. We likely need a smarter approach. Instead of checking every single subarray from scratch, let's think about efficiency. Maybe we can use a sliding window. Imagine we have 2 pointers, a 1 and a 1, defining a window within our array. We'll also need a way to quickly know how many distinct numbers are currently inside this window, maybe using a frequency map or a dictionary. We start with both pointers at the beginning. Then, we move the pointer, making the window bigger, and updating our count of distinct elements. Now, here's the clever part. We keep expanding the window by moving as soon as the window from 2 contains exactly distinct elements. We've found a complete subarray. But wait, there's more. If the subarray from 2 is complete, think about the subarray from 2, right plus 1. It must also be complete, right? It contains all the elements from the T2 window, plus 1 more. It still has at least distinct elements, and since is the maximum possible distinct elements in the whole array, it can't have more than, so it must have exactly 2. The same logic applies to the subarray from 2, right plus 2, and all the way to the end of the array. How many such subarrays are there starting at and ending at or later? If is the total length, it's n minus right. So, once we find that first complete window ending at, we can immediately add n minus right to our total count. Then, we shrink the window from the left by moving the pointer forward and update our distinct count, and continue the process. Alright, here's the Python code that implements this sliding window idea. It might look a bit dense at first glance, but it directly follows the logic we just discussed. We'll break down the key parts next so you can see exactly how it works. No need to feel overwhelmed. First up, the setup. We get the length of the input list. Then, the crucial first step. We figure out our target number by creating a from the numbers, which automatically handles duplicates, and getting its size. We initialize our final answer to 0. Our pointer starts at the beginning, index 0. And we create an empty frequency map, called using Python's counter, which will help us keep track of how many times each number appears within our current window. Next, we have the main loop. The pointer goes through each index of the array, from 0 up to n-1. In each step of this outer loop, we effectively expand our window to the right. We take the number at the current position, nums right, and we increase its count in our window_counts map. Then, we immediately check if our window has become. This loop is key. It checks, does the number of keys in our window_counts map, which represents the number of distinct elements in the current left-right window, equal our target total_distinct? If yes, the window is complete. And remember our insight. This means all subarrays starting at the current left and ending at this right or any index further to the right are also complete. The number of these is n, right. So we add n, right directly to our total count. After we've added the count for the complete window starting at left, we need to try shrinking the window from the left to see if shorter windows starting later are also complete. We take the number at the left pointer, nums left, and decrease its count in our window_counts map. If that count drops to 0, it means this number is no longer in the window, so we completely remove it from the map's keys. Finally, we increment left, effectively sliding the window's start point one step to the right. The loop condition, len, window_counts, equals total_distinct, will then be checked again. If the window is still complete even after removing the leftmost element, we repeat the process, add n, right again, because the window ending at right is still complete, just starting one step later, and shrink from the left again. We keep shrinking until the window is no longer complete. Then, the outer loop continues, moving right to expand again. So how does this sliding window approach stack up against the brute force idea? It's much better. In terms of time, both the OA and pointers move across the array essentially just once. The operations on our frequency map, adding, subtracting, checking size, usually take constant time on average. So the total time complexity is basically proportional to the length of the array. We call this big O of n, or order n time complexity, very efficient. For space, we need that frequency map to store the counts within the window. In the worst case, it might need to store an entry for every distinct number in the array. Let's say there are distinct numbers. The space complexity is quote, 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 S case. Okay, let's quickly recap. The problem asked us to count subarrays, those having the same number of unique elements as the original array. We saw that simply checking every single subarray would be too slow. The winning strategy was the sliding window approach. We used 2 pointers and a frequency map to keep track of distinct elements in the window. The crucial insight was that once we find a complete window ending at, we know that all subarrays starting at and ending at or later are also complete, allowing us to add quote minus right to our count and then efficiently shrink the window from the left. This clever technique brought the solution down to a very nice order n time complexity. Hopefully that breakdown made the problem and the sliding window solution much clearer. If this explanation helped you out, please hit that like button, consider subscribing for more LeetCode walkthroughs, and feel free to leave a comment if you have any questions or alternative ideas. And hey, if you're feeling extra supportive, the Boba Fund is always open. Keep practicing, keep coding, and I'll see you in the next video.